Bismillah. Thank you very much for this clear presentation. Let me just make a comment first that this, what we call hyperbolic equation, go back to in history for a long time. So you mentioned only like recent literature, but if you go, for instance, of the team of CMU, you can find Gorton, Coleman, and those people who work on what we call second sound. So probably later on, when you want to work on this area in your PhD thesis, whether here or somewhere, you have to go a little bit in history and to see why this has been introduced. And over there, you can see a very strong and solid theory. Now, let me ask you a question. If you go to page, I think, if I'm not mistaken, 10, for instance.
10.
Yeah, you go back all the way. 10 and 11, where you started with Fourier's model.
Oh, okay.
That's
Yes. This one?
No, Fourier's model. It's you presented in the beginning. Yeah, this one.
Yes.
Yeah, this one. Go one page first.
One page?
Yeah, forward.
Okay.
Here, this is the hyperbolic
Yes.
model. Now, you said this one exhibits a finite speed of propagation.
Yes.
What is the speed here?
You mean which constant?
Yeah, you just give me the speed of propagation of wave-like heats.
Yes.
These are some heat that goes like wave, not
I see.
okay. So what is the speed?
Well, this is C is the speed.
The speed is
Here, this.
yes, it is c squared.
Yes.
Sc is the speed.
Yeah.
Oh, very good. Now this is clear. It is finite.
Yes.
Now if you go back to the Newtons,
Okay.
you said infinite speed. Why?
Why infinite speed?
Yeah. How can you show
This
people
is-
here? They want to see infinite.
Okay. They want to the infinite speed.
Yeah.
C is if C is 0, that coefficient here,
Yeah.
it's infinite, so it disappears.
What do you mean?
If C is infinite, it will disappear.
Okay. Oh, very good. This is what I want to say. Very good. So with this very large infinite speed, this term is disappeared. So that's why we have this.
Yeah. Okay.
Yeah. For infinite speed, C is becoming large. No, this is 0.
Yeah, you mean the coefficient will be 0. That's what you meant.
Exactly.
That you need that. Very good. Now, if you go to page 37, I would like to ask also a question here.
The final example. Yes. Okay, 37. 37. Sorry.
No, don't read it in Arabic. Read it in English. If I'm not mistaken.
Okay. This one? Is it an equation or a graph?
I think an equation. Well, if you go a little bit down, or okay, it's okay. I just want to mention here that if you look exactly to your equations,
Okay.
yeah, go to one of these equations
this one, for
before these
example.
graphs. Yeah,
Yes, but this one, for example, this one.
this one, for
Yes.
instance. Yeah. Now, this is a hyperbola.
Yes.
And under some conditions, you saw that the temperature versus time would go to 0.
Very good. Yeah.
Can you explain this? Why did you get that?
Well, the vanishing behavior of the temperature versus time is due to the source, because we don't have any source of temperature in the boundary. Because the boundary condition assumed here, all is 0. Yes, this is the boundary condition. We don't have, let's say, any external source, except the laser source, what I mean. So, and the nature of that source is just for, unfortunately, I didn't graph it, but the graph of the source is just for a period of time, then we stop heating. So that's why we expect the temperature for a large period of time will vanish due to the nature of the source model.
How about if P, you go back to your equation?
Okay, this one.
No, your equation, don't go. Yeah. How about if P is 0? Do you expect to have?
Okay, this B.
Yeah, if that P is 0.
You mean if we don't have the first
If you don't
derivative
have
of time?
that. If you don't have that and just ignore its S for a time, what would be this equation? If you ignore it for a time, ignore S for a time and B is 0, then your equation will be like what?
Wave.
So usually your equation, they die at a long time, they don't die.
Very good, yeah. That's why the thermostress shows the wavelength. Because the thermostress is a wave equation.
Yeah, I'm saying,
Yeah.
don't you think that also the presence of this damping term,
So this is the damping
term
factor.
for that equation?
Right. Which will then...
And you started with a small, because that damping will have no effect if you started with a high source. Then that might blow up. Okay?
Okay,
But
you mean if we start the heating initially from high?
It blows up if B is small.
That's what
But
we
not-
started.
Yeah, but you
Unfortunately, I
started with a
didn't grab
small.
it.
So the damping, this term,
This one.
so the equation, though it is hyperbolic, what it dominates is the parabolic side.
Very good.
That is what
I
happens.
get it, I get it. Even the nature,
Can
okay,
I
go.
interfere?
Yeah, please, yeah.
B is in fact, rather than damping, we call it the storage theorem. Actually, what happens, whatever the energy that you put in, is a semi-infinite domain solution. And by this stuff, so that certain depth positive and infinity. So whatever the energy that you put into the system, rather than dumping, it is stored within the material. The reasoning is the energy cannot be destroyed. It cannot be, so it remains as stored. So the B here, if the B is larger in reality, the storage capacity increases, so you dump quickly.
Yeah, I dump it quickly, definitely. Please, yeah.
So if the first if the source term and the B goes to be zero, it will become like a wave equation with an elastic. So we don't need to worry about it. But this B represents here the storage term.
The source function here is S of xt, right? It is a volumetric source.
Yeah.
What if you replace that with something else like microwave source? Or feed.
What do you mean by
Microwave, does it give heat or not?
Well, I think it's a really technical.
Now the source is laser, right?
Yes, it's a source.
Replace that with microwave.
Can I interfere?
Yeah, but this is engineering.
Then we calculate on
No
that.
mathematics.
Yeah.
Because I'm not in this area, and that's why I'm asking.
So for us, it's just difference between the exponentials.
So we have to model microwave first mathematical experiment.
Yes, exactly.
I think it's Professor.
Fala, Dr.
Yeah. Actually, what happens is that the source term here is like a gas distribution. It is an exponential decay in terms of space. So it is first to start by Lambert. So we call it the Lambert period. It means that the radiation is in such a way that it is like a coherent nature. It means it should not diverge, neither converge at any point. It should be all in parity. So in the space, it decays exponentially. So the intensity, we do not worry about the dispersion of any other kind. The microwaves, also there is another term in the exponential which is called minus delta x. It says how it decays along this axis delta. Delta is called absorption. Yeah. This is called absorption coefficient, 1 over absorption delta. So it tells you how fast it decays and how sharp it decays, how much. So rather than time, the space-wise variable. If it is the ultrasonic waves or some other waves, it behaves similar, but the delta value will differ. When it differs, so it decays either very early, like it becomes like a surface heat source. In the microwave, it is like a surface heat source, which here delta will become in such a way that so large that exponential minus delta is supposed to be like what we call 0 to 1. So that one will make it the source term will not be like a volumetric term which is decaying. So depends upon the physics of the problem how you look at it actually. Because all physics and mathematics correlate.
Any other? Yeah.
First of all, I would like to say thank you very much for this very nice presentation and really very clear. Wishing you the best, and inshallah ta'ala in the soon future we'll see you a professor. In slides number 5 and 6, when you start defining, your stuff here, always saying if it exists. In reality, what's happening? It's not.
Yeah, ask Hassan. He will ask.
He is a
He is
mathematician.
supposed to know.
I know the answer, but let him tell me
Yeah.
how the function will behave. Yeah.
So what will happen?
That's the answer.
What do you mean?
When does it exist?
Yeah, but
Okay, what's the condition for existence?
Yeah.
For Laplace transform, of course, the condition for function to have a Laplace transform, it should have some exponential. It should be of some exponential order. That is, the modulus of this function is less than some coefficient times some exponential, which is very huge. So this is the condition of that. As for the Fourier transform, should be, I think, L1. Should be L1 integral.
So is it possible in the same period that we will have something in between that does not exist, and if it's possible, what will happen here? What will happen? Yeah. Because in reality.
Mathematics point of view, the function can be analytical if there is, if derivatives will not be zero or there is no singularity in the function.
Yeah, that's it.
Now, this will happen when you have the nonlinearities. This is why you cannot use the Laplace transformation in nonlinear differential equations. It fails because it does not satisfy such situation. So you do not have the proper analytical solution or proper analytical function which represents the physical behavior. So this is where the failure. But there existed, yes. We look at it from the differential equation. If it becomes nonlinear, then our privilege is that use other techniques like perturbation method, which we did earlier, or some other method.
The Fourier transform of 1 will not exist.
Yeah.
Of course. Yes.
Any other questions or comments, please?
I'm seeking an information for. The last integrals, you said these are complicated integrals.
Yes.
When you said this, do you mean you don't know whether they converge or not?
No, what I mean, let me show you the expression first.
Yeah, it is really expression. I mean,
Yeah.
complicated
For
expression.
example, let's see.
Yeah.
For
Do you have an
example,
idea if they converge or not, or under which conditions?
Yes, the only difficulty in fact of this integral, first of all, they are treated under complex sense, I mean complex approach. Because this is the Laplace, and even for you can consider some control. The only issue with such integral really is what we call the non-isolated singularities, the branch points. This is even, by the way, this is the major issue with hyperbolic heat conduction equation. Like for example, see this square root. See this one? They are at alpha square, so that means we have 2 branch points. Unfortunately, as I was investigating these 2 branch points, infinity was not even isolated, which is more worse. We cannot use the residue at infinity. So these are 2 branch points, even the residue at infinity cannot be used. So this is the issue with these, is really the branch points. These, the square roots, is giving us tough time in terms of analytical solutions. These are the major type. That's why I used even numerical approach in the previous integrals, because of the square root. Because of the square root. And this square root is involved. It's not even of one, let's say, type. It's not branch points.
Practically, we usually say that, okay, we choose that branch point which makes a single value and do not pass our control crossing the line joining to branch points and so on, and then the integral will exist. But
Yeah,
to do it practically.
Yeah, I'm talking practically, because if this does not, give you anything, especially for practical, then in this case, it's
Some
meaningless.
numerical approximation for some conditions. Yes.
Can you go back to that slide where you had most of these functions here? Yes.
This one.
Thank you so much.
Yes. No.
This one.
Yeah. Okay. Do you expect us to read this or to comprehend?
No, there is.
1 minute or 2 minutes? If not, why do you have it here?
Yes, by the
Or
way,
just to show us?
no, I want to show you these 2 nice things. Let's end this. I want to show you just in the solution, this will gonna contribute the results. The result to show that we have only at the window we have graph. Before this we don't have. This is because of the Hibside functions.
Could this A, could this B, and have a very nice
Okay, this is
that we can.
When you touch the practical problems, you got such a line. If you like f and g functions less than then you get f and g. But practical situations have solutions.
This is general defense. You expect people, they cannot read.
No, it's okay. I think it's okay, because we would like also to see how complicated this is.
Yes.
Yeah.
At times, we
You want to impress people, huh?
Okay, any other questions, comments? I thank you very much for this presentation and thank you all.
I would like like to even welcome سعادة الأستاذ إبراهيم محمد آل الشيخ. He's graduated from KFUPM, so you are very well. جزاكم الله خير.
There are some refreshments, so we make a break for refreshments.